The topic which we are going to see is a rotation of rigid body. Before going for a rotation of rigid body, we can see what is meant by a motion. Motion, we all know that it is a movement of an object from one place to another place. For example, when we kick a football, the ball moves forward moves in a forward direction. That is a translational motion. When a ball is moving, it rolls around. That is it rolls about an axis from the center. It is called rotational motion. So that is the translational motion and rotational motion. Translational motion, the body moves in a straight line, in which case all the particles in a body move along a straight line and it have a equal displacement and in an equal interval of time, so that we can say that all the body particles in a body will have same velocity and acceleration. That is, for example, movement of a car or a bus. That is, the peoples or persons which inside a bus also moves with the same velocity and acceleration. The coins on a carom board, it also moves with the same velocity, that all the coins will be moving with the same velocity and acceleration. Apple falling from a tree and the cat walking, these are all the examples for translational motion. Rotational motion, it is body moves about a fixed axis. That is, axis, it will be a fixed one. So the body will be moving in a from a fixed part to another part. So that is, it moves with the concentric circle about an axis. For example, if we take a door, one side of the door will have a hinges, other side we can open it. So the body, that door moves from a one part with the center axis on a one side, from it is moves in a half centric circle. That is the thing. The different particles, that is, the door also have been the rotational motion, the object also has a different particle. All the particles will have different linear velocity, but the angular velocity will be same. This is the thing. These are the examples of rotational motion. That is, motion of the door about its hinges, wall or pulley in a vehicle or machinery, for rotation of blades in a fan, rotation of CDs and DVDs in CPU are the examples of rotational motion. Now, we can see about a rigid body. What is a rigid body? Rigid body is an object which has definite shape and size that does not change due to any external force. When an external force is applied also, that shape will not change. See, for example, if we take a block, there are number of blocks are stagnated on a particular point. When a force is applied to it, that shape will not, it is not affected by what? The force. That is the thing. In other words, the body can be defined as an extended object in which the distance between particle is not altered during a motion. That is, the object shape is not getting altered. Only its position is getting changed. So in a rotational motion, so now we can see about what is a rotational motion. Rotational motion in a rigid body. That is, rotational motion in a rigid body is considered as a stationary motion. And here, the rotation is caused by a couple acting on a body. Couple is the force which is acting on a body. So its state can be changed only by applying a couple or a set of couple, not by any other force. So, for example, so we can consider a rigid body. This is a rigid body. This rigid body revolves around its axis with the velocity, with an angular velocity omega. We are considering two particles, that is particle 1 and particle 2. It was at a distance of A, that is, it was at the this particle revolves in a circular path about a point. This is point in an axis. That is a point A and point B in an axis. The thing here, it is found that center of each circle lies on a OY. The center of each circle lies on a OY, and the radii of the circle AP1 and AP2 will be equal to a perpendicular distance OY. It is equal to the perpendicular distance OY. So when it is we know that in a rotational motion, though the particle will have different linear velocity, it will have a same angular velocity. Therefore, all the particles rotate about an axis with an angular velocity, the dt, with an angle d theta, with an interval of time dt. So the angular velocity omega is equal to d theta by dt. The corresponding angular acceleration, or that is the rate of change of angular acceleration, alpha is equal to, alpha is rate of change of angular velocity. That is d omega by dt. And then What is rotational kinematics? That is rotational kinematics. Here it really gives the relationship between angular velocity, angular displacement, angular acceleration with respect to time. It describes the rotational motion of a particle without considering a mass or a force that affect a rotation. That is, a body's mass or a force which is applied to a body. The rotational motion of a particle will not consider the mass or the amount of force applied to a body, and it is not affected. The rotation is not affected due to it. The rotation of kinematics of rotational motion for a constant angular velocity with respect to an axis of rotation is analog to kinematics of linear motion. That is, we have two types of kinematics. That is, one it is kinematics of angular rotational motion, and another one is kinematics of linear motion. Here, the kinematics of rotational motion for a constant acceleration with respect to an axis is similar to the kinematics of linear motion. That is the thing which we are proving over here. These are all the equation which gives the relationship between rotational motion and linear motion with respect to displacement, velocity, and acceleration and time. So here we have linear motion and here we have rotational motion. The linear motion Vf is equal to Vi plus At. That is, similarly, Vf is the final velocity, Vi is initial velocity, A acceleration, T time. It is given by another notation in a rotational motion. Wf, omega f is an angular velocity and omega I is an initial linear velocity. Alpha is an angular acceleration, T is the time. Similarly, with respect to S, that is the displacement, Vi T is equal to half AT square. See here, the theta is displacement. Theta is equal to omega I T plus half alpha T square. And Vf square is equal to Vi square plus 2AS. Here, omega F square is equal to omega I square plus 2AF. These are all the relation between, that is, equations that governs linear motion and rotational motion. Now we are coming for a main part, that is the rotational kinetic energy of a rigid body. So here we are considered a rigid body. This rigid body rotates about an axis x dash with a constant angular velocity. That is, the velocity of rotation is same. All the particles in a rigid body, all the particles in all the rigid body will have a same angular velocity, but the linear velocity is varying. We know that linear velocity V is equal to omega r. R is the radius. The radius of a particle 1 with respect to x-axis is r1, and the radius of the particle 2 with respect to x-dash axis is r2. It is varying. Since the radius is varying, the linear velocity will get varied. So here the velocity v with the radius varies with respect to a radial distance from a x-dash. That is, radial distance of a particle from the axis x-dash. So here we can consider there are n number of particles or I number of particles. So each particle will have different linear velocity. That is, let Vi, V1, V2, V3, etc. up to Vi be the linear velocity of the particle, and of mass M1, M2, etc. Mi. It is rotating about an axis of rotation at a distance R1, R2 up to Ri respectively. So this is the velocity we have known. We have known about a radius. So what is the kinetic energy formula? We all know that it is half mv square. So kinetic energy of the particle 1 with the mass m1, it is equal to half mi vi square. Kinetic energy of the particle with the mass m2, it is half m2 v2 square. And then here the total kinetic energy of the all particles will correspond to the total kinetic energy of a rigid body. So the total kinetic energy is equal to what? The total kinetic energy of all the particles. That is, particle 1, we all know that it is half m1 v1 square. Of particle 2, it is half m2 v2 square. And etc. up to particle I, we can say that half mi vi square. What is V1? R omega. What is V2? R2 omega. What is Vi? Ri omega. Substitute all these values in above equation 1. When we substitute this V1 values in above equation, we get the total kinetic energy as half mi Ri omega square plus half m2 r2 square omega square, etc. up to half mi Ri square omega square. In this, what we can do? It is the summation of. In general, the above equation can be written as half summation of I equal to 1 to n mi ri square omega square. What is the summation of MI square? We all know that, of course, it is a moment of inertia. So it is denoted by the symbol I. So the total kinetic energy is equal to half I omega square. So this equation represents the rotational kinetic energy of a rigid body.